So this is a continuation of my last video where I showed how to make a character exported from Blender into Unity walk up and over an uneven surface. So this was the plane that we used in Blender to just make a very simple hill and our spider character that walked over the hill. And check out my channel if you want to see that video. I'll put a link in this video just if you want to see how we did that part, because this is going to take that and continue on from it. So the first thing we need to do is we're going to come in here and let's grab our spider. Let's grab him, Y direction, move him out of the way. So what I'm going to do is I want to take this plane and make two simple hills out of it. So the first thing I'm going to do is I'm going to select everything and I'm going to scale the Z direction 0. I went over this in my one video where I exported the rocks. It's a handy way to flatten things out. So now I got my plane. And what I want to do is I want to subdivide it just one more time in order to give us a few more planes to work with. I'm just going to grab it all, grab in the Z direction just to move it above that plane so we can see the grids a little bit better. So I'm going to grab this in the Z direction, make a simple hill. Then I'm going to make a second hill here, a little taller. Then what I'm going to do is I'm going to grab one of these faces to make a little steeper. Oops, let's make that smaller. I'm going to make a steeper angle, and you'll see why. So essentially what we're going to do is when the spider comes and encounters the hill, it's going to look at the angle of the faces and determine if it can climb up and over. If that face is greater than a certain angle, it is going to have to decide, should I go left and should I go right? And so what we can do is look at the faces around it and determine which one has the lower angle. So if it encountered the face here, it would check this face. This is at a greater angle than this face, so it would decide to turn left. If it comes in here and sees the exact same angle, then we have to decide. Maybe it always goes left or always goes right, or maybe picks a random number to decide whether to go left or right. We can make that decision when we're making our script. So this is going to be our basic test plane that we're going to export into Unity. So what I'm going to do is I'm going to export that into our Unity project. I'll save this quick first. Let's go back into object mode. And I'm going to export it to Unity. And then we'll hop into Unity and start taking a look at our script in order to determine how we're going to write that script or add to that script in order to get the functionality we want. So we'll do that next. So before I can export into Unity, one thing I forgot is we need to reset the UVs, because when I did all that work on the plane, it would have been reset. And we need to do that. So if we hit reset here, and if we go back into Unity UV editing, we can see now all of the bounds, all the UVs are now the full boundary, which is what we want in order to get our our material to map correctly into our plane. So let's go back to layout, export, FBX. I've pathed. I'm going to copy it right over my old plane. And now we go back into Unity. Here we go. We can see our plane now is back in Unity. So if we grab our spider, oops, didn't grab the spider. Drag him over here. Maybe scale him down a bit. There we go. So now we're ready to dive into our script and figure out how to make him walk up and around these hills. And then we can test out using the two different hills our decision making of whether he turns left and right. So we'll dig into that next. So we're going to take a look at this script code. So before I start, just a quick review of what we did in the last video, which was walking up and over a slope and matching the angle of our object, whatever character we are walking over the slope, to match that slope. So just a quick review, we had this run speed, and that controlled how fast he was going to move forward so we could match that animation of his legs. Rotation step amount, which was, remember we didn't snap to that new angle of the body directly. We did a slurp, so this was how fast it would do that rotation. And then we had that leg distance, doing rotation, start angle, end angle, and rotation step that controlled the actual rotation of the body to match the slope he was over. Then in the start, we grabbed the armature. We found the leg direction so we could properly place it above the slope. And then during that update, we would do the slurp rotation. And then in the fixed update, we would do this raycast, which would check the angle of the face that we were over and start that rotation to match the body angle with the angle of the face we were over. And just a reminder, this is doing a lot of rotation with quaternions. I do have two videos that go in depth of how to use quaternions and how all the angles work, because it is complicated, so I'll put those links in. If you're confused or having difficult time understanding what we're doing with some of these angles. So what we're going to do is we need to know a couple things. One, we need to know the slope right ahead of our object. So say the spider's coming up to this slope, we always want to check the slope right ahead of the object. How far ahead is a question. So I chose to take the full body length of the object that we're walking, the spider in this case, and I will move that far ahead. So I'll always be looking about a body length ahead of the spider to see what the slope is. And then once we determine, say he comes up to here, he checks this slope, he's going to check the slope to the left of it and to the right of it to decide which way to rotate. So say, for example, he was over here. And you got to be able to visualize this when we're looking at the code, is that it's going to check the angle. This is, say, a steeper angle than over here. He's always going to want to turn in the way that the angles are less steep. And that's just how I chose the logic. You can do whatever you want, but that's what I figured. You're always going to want to go around to the lesser slope. If they're equal, it probably will end up being whatever slope he checked first. I can't remember how the code's working. And we need to know a couple things. What is this max angle? I can set it to wherever I want. It can be 10 degrees, it can be 90 degrees, whatever it is you want, and that's going to be a field. And then what is the angle to check? It could be a fixed angle. I made it a field variable simply because while we're playing around to see how the spiders move over some of these irregular objects, we may want to modify that in order to get a better result. So having that field is nice because you can simply watch the spider's walking and modify those fields until you get the result you want. So back to the code. We have a couple functions that we've made and a couple of new variables that we've created. First of all, we have these new field variables. So this max angle, this is the angle of the slope ahead that you want to walk around. So anytime it's greater than 100 degrees, it will, remember 180 is straight up and down. So I just defaulted to 100. We can play around with that. The angle left is going to be negative 30 degrees and the angle right is going to be 30 degrees. Again, these are just defaults that we can modify. And then in the start, what we're going to do is I got a couple of variables that I created, member variables. So we have the ahead check. So this is the distance ahead that we want to check. Remember, we're going to make it that body length. And then we have the current rotation right and the current rotation left that we're checking for those angles. And in the start, it's going to compute this ahead check is going to use, it's going to find the transform of the cube. So our object can have multiple items within it. Again, the actual mesh, I didn't change the name when I made it in Blender, and so it just started out as a cube, so it's just called cube. Again, you can name it whatever you want in Blender, but you got to find the actual mesh, and this is versus the armature or other items within your object you brought in. And then I'm going to get that skin mesh render from that mesh, and I'm going to call it MR, and then I'm going to use that in order to get the bounds. So that MR shared mesh is actually the mesh components, and it has a variable called bounds, and I'm going to get the Z extents. So the Z extents is going to be the item ahead. And maybe if we just take a quick look at our spider, we see this cube. See, the spider object has two children. One is called armature, the other is just called cube. So this is the name we're searching for in our script. So I've got that ahead check, that distance ahead from the body, and then I'm going to just rotation left and right, we're going to be setting. So I just make new quaternions. Technically, I could get away with not making them globals. I don't know how expensive creating quaternions is, but we're going to be creating them and using them a lot. So just making member variables just makes things easier. So now let's come down to the actual functions. So I've created three functions here. The first one called get angle of slope ahead. So this is going to get the angle of the actual face that's ahead by one body length. So I'm going to get, first of all, I'm going to get the point ahead. I want to get the point in 3D space, and I'm going to transform direction. Again, this makes Z forward. And remember, just a quick reminder that right now Z is forward, right, with my spider. This is the Z direction. But if I rotated that spider, oops, got the wrong one. There we go. If I rotated that spider, see, Z is still pointing in this direction because this is in global coordinate system. You got to remember in rotation we have global coordinates and direction, and then we have local. So this is the local direction from that spider, and actually we can change that if we go up here to local. See, now this is in local coordinate system. This is what we want. We want Z direction always to be pointing in the same direction as our object, in this case the spider, is facing. And so that is why we always use this transform direction, gets the Z direction in that local coordinate system. And we're going to want to, in the local coordinate system, 0, 0, 0 is the X and Y. I don't want to change those. I just want to go ahead by that ahead check, that one body length. So that is going to be a point in 3D space that's directly ahead of the spider. Then I'm going to want to do that same ray cast that we did when checking under the spider, but now it's going to be ahead of the spider, and I'm going to want to grab that angle, and then I'm going to want to just return the angle. What I did is it was just easier to use the spider's transform, and it's actually, the transform is actually going to be modified. So I want to just save that transform, and then I just want to restore it after I've modified it. So we don't want to actually rotate the spider during this function call. So the next thing we want to do, oops, I kind of skipped ahead, looking at the wrong part. So this actually was that transform direction and getting the angle of the point ahead. This get angle left is going to do the exact same thing as the slope ahead, except it's going to want to check ahead and to the left by some angle. And that angle is going to be that field that we used. So here what we do is, again, we save that current rotation. We get the rotation left. We set the Euler angles. And setting the quaternion through Euler angles is easier sometimes. Setting it fixed using just the coordinates, those 4 coordinates, can be confusing. I find it confusing. So it's easier just to use the Euler angles, which is easier to picture in your head, that X, Y, Z. And so what I'm going to do is I want to get that rotation, and I'm going to rotate around the y-axis. And remember, the y-axis is straight up and down, so that's going to rotate that spider. Just a quick reminder, remember the green is the y, so it's going to rotate our spider around that y angle by our angle left. In this case, it's going to be that 30 degrees, negative 30. So then our transform rotation is going to take our current rotation, which is the how the spider's facing currently, and multiply it by that rotation left. And if you looked at my other rotation videos, you'll know that when you add angles, multiplying 2 angles together, quaternion angles, actually adds them together, and dividing actually subtracts them. So in this case, we want to add these 2 angles together, so we use that multiply, and that gets us our new rotation left. Then we're going to come here and we're going to rotate, or get our transform direction, get the angle he's currently facing, and then we want that point ahead is going to be use that same transform direction. Actually, looking at this code, this dir isn't actually used. So I kind of must have modified this along the way, but we're actually setting our new rotation with that new rotation left, and then we really just need this line of code. So we can actually delete this while I'm looking at it. So our point ahead is, we've already rotated the spider to the left, and then we're doing the check ahead. We're gonna do that same ray cast, get the angle, again, set our rotation back to default, and then we're gonna return that angle. And then the get rotangle right is actually gonna do the exact same thing, except it's gonna use that check angle right. And let's just do a quick check. So check angle right is 30 degrees. This is the other thing you got to remember is what is the positive direction and what is the negative direction. So clockwise is going to be the positive direction. Counterclockwise is going to be the negative direction. So that's the other thing we got to remember all through this, which way is positive, which way is negative for those rotations. So now that we have our functions to check the angle ahead and check the angle left and right, we can use these in order to make a determination if we need to move left or right. First of all, by checking ahead, and then deciding which direction we want to try to rotate that spider, left or right, by checking those slope angles to the left or right. So we'll add that code next and take a look and then try it out. All right, so now what we're going to do is we're going to add code to check that ahead angle and the angle left and right and decide what to do, and then integrate that new rotation into our rotation that's rotating the body that's parallel to the face. So the first step is to check ahead and see if the angle of the face ahead is too big. So we'll use those functions that we just talked about. So we get the angle of the slope ahead, and then we're going to check if that angle is greater than max angle. Remember, the max angle was that field that we can set to whatever we want to decide how steep we can walk over. So if it's greater than that angle and we haven't just rotated, so if we're in the middle of a rotation, we don't want to keep checking this. So we want to complete that rotation before we check again. So he's going to kind of be walking and rotating for some distance before it's going to check again. So there is a chance that it actually hits and tries to go onto a slope that's greater than max. But that rotation happens pretty quick. And again, this code is not meant to be 100% perfect. It's to get a look of walking around whatever steep angles exist. So then what we're going to do is we're going to get that angle of the slope to the left of us by that angle, which is that 30 degrees to the left, get the slope 30 degrees to the right. And then what it's going to do is, again, this is assuming that we need to turn left or right. It's going to say if the left angle is less than angle. So say, for example, the angle in front of us was 110 degrees because we set the max angle to 100. The left angle has to be less than that. If it's bigger than that, there's no point in turning to that direction because it's actually too big. And the left angle is less than right angle, meaning if the right angle is smaller, we would rather turn to the right. And the left angle is less than max angle. Because, so basically, if you hit a straight wall where all the faces were the exact same angle and it was bigger than max angle, this logic isn't going to work. We'd have to do some other special case stuff. But in this case, I'm making kind of some general mountains. I'm not having straight walls, so this isn't going to handle that case. So if that is true, then what we're going to do is we're going to take this distance traveled since rotation. So what we want to do is after we rotate, we don't want to check right away. We want to travel some distance, and it's going to be the distance of a body. The Z ahead. So we want to travel at least as far as we checked ahead before we want to check again, because checking 1,000 times a second really isn't necessary. So then we want to say just rotated is true because we're going to be starting our rotation, and then this is a new variable that we added, and that's going to be the amount of rotation we want to achieve. And in this case, it's going to be 30 degrees because that's what I set my left rotation to be. So if that's not true and the right angle is smaller, So remember this had to be true. The left angle had to be less than right angle. Then we want to check the same thing for the right angle and set those same variables. So if it's smaller angle to go to the right, we're going to turn to the right. If it's smaller angle to the left, we're going to turn to the left. If we hit both left and right are too big, we're not going to do anything. So technically this would, if you had a flat spot that it hit, it would just try to walk up and over that. But then it's going to wait. As soon as we hit a not flat spot, it would turn left or right. Again, if you had a perfectly vertical wall, it would actually climb up and over that wall. It's not going to try to go around it. Like I said, you'd have to add a special case for that, which I didn't do for this demonstration. So we've got our new current rotation Y. So now we come up here and we've added a couple block of new code. So before, all we were doing is we were using this rotation to align with the slope, and we are calling this start rotation. And actually I've added this block of code. So this block of code integrates that current rotation Y that we just set, and we've created another Euler angle, and we've multiplied that by our new rotation to get this new world rotation. And remember, multiplying is adding. So we're adding in that rotating around the Y axis. Again, this Y axis is going to be in local coordinates, and so we got to convert it to world coordinates. So I called it this world rotation. Again, all this rotation math is explained in my other videos at great length, so refer to those if this is getting confusing. So then what I want to do is I want to say, is this new rotation different than my current rotation? So I'm going to take my current rotation, the X, Y, Z Eulers, and I'm going to compare them to my new world rotation, because if it hasn't changed, there's no point to start a new rotation. It's just we're fine, we're on a surface, and we're not going to be changing rotation at all. And we're not currently in the middle of doing a rotation. So if we're not, if all these are true, we're going to want to do this start rotation. Again, which is the same thing we went over before for the rotation. The only difference is we've integrated this rotation around the Y axis to make him turn left or right. Now, a couple other things we've added is we got to add this just rotated. So what we want to say is if we've traveled, if this distance traveled since current rotation is greater than a head to check. Remember, a head to check basically is the distance of his body. So if he's traveled more than the distance of his body, we want to change this just rotated to false. So maybe the rotation finished, maybe it didn't, but if we've traveled at least the length of his body, we want to set this just rotated to false. So then we can then check again, that check ahead and that check left right is going to happen. So this basically says, hey, finish your rotation, make sure you've walked a certain distance, and then start checking ahead to see if we need to turn left or right. So this is that smooth rotation code, which we went over in the last video. So this pretty much is all the code to check left or right. What I'm going to do is drag that off. We have our spider here, and we are going to run that code. He's going to go. He's going to turn left. And then he's just going to keep on going. So if we move him over more this direction, let's see, he should turn right because that left angle is bigger than the right angle. Yep, and he turned right, and then he kept going. Go back to the scene. So the issue here is that they now are all, if we had a bunch of spiders walking, they'd all just, they wouldn't walk over this, but they're not going to walk around it, right? Because they turned and they're like, hey, I'm not hitting anything that's too steep. I'm just going to keep walking in that direction. But that's not what we want. What we want them to do is have a destination in mind. So I'm trying to get to my destination. This hill is in the way and I don't want to walk over it. So what I'm going to do is I'm going to turn to make sure I don't go over something too steep, but then I want to turn back. I want to keep trying to see if I can get to that end point. So just to review these numbers, so I set my max angle to 50. That check angle left and right are 30. These two, this rotation, step them on, and run speed, I had set on my previous example. So if I set this like to a big number, like let's say 80, we can see the difference of what happens. So now he should go further up the slope before he starts to turn. I don't know if any of these are bigger than 80. So none of those actually were actually bigger than 80. Let's set it, let's try 60. See what happens. So it goes up. And actually these were actually probably greater than 60, so wasn't a great example. But like I said, you can change that max angle and adjust it to decide how steep of an angle that he can walk around. I just want to do a quick double check here just to make sure that that angle ahead is working. Now he should try to walk up here. Oh, actually, that's not working. That's interesting. So it worked in this direction, but not in that direction. I've never actually tried that. I'll have to take a look to see what the problem is and see if we can fix that. All right, so I did a quick little debugging session. And one thing I was thinking that straight up and down is 180. Straight up and down is 90. So I had the max angle at 60. So what I did in order to debug this, and it's a easy debugging trick, is what I added is get angle of slope ahead. I added this debug log that would just print the angle to the console window, because that's what this does, if the angle doesn't equal 0. And so what we can do is, if we then go and run this is about where it was. I had it at 60. Let's clear the console window. And then if we run this, we can see now the angles get up to about 58, got up to 61, but this angle, you see it only got up to 55. So it looked like it was gonna be steep enough for him to turn, but it actually only got up to 55 degrees. So it actually was working correctly. Even though it didn't look like it. So this debug log, especially for situations where you want to see something continue to run, so you don't want to hit breakpoints and have to step, because that doesn't really help. This debug log can really help you debug, especially things like this where you're trying to figure out what's going on in the different situations. So now that we got him turning correctly, now we can add our last piece, which is to make him actually continue toward a set destination. So what we're going to do is I'm going to make insert an object, and I'll call it nav marker. and we'll get that location, and we'll add some code to have him continue to try to turn toward the nav marker. So let's dig into that next. So what I have here is our scene, and what I've done is I've added an object. It could be any object. I just made it a simple kind of pyramid. I colored it yellow, and as you can see, it's called nav marker. It has a tag, I should say, that's called nav marker. So if you're not going to have a tag, I had to do add tag and add this nav marker before it added to the list. This list is just kind of a default that Unity gives us for tags, and I added a new one called nav marker. So that's going to be the exit point of my spider. So I always want to walk toward that point no matter what, and no matter what I'm going to do is, as I walk around these tall objects, I'm always going to want to try to turn and align myself toward that marker. So what we're going to do is look at code on how that's going to happen, and it's a little complicated. It's similar to the code that we used for walking around the tall object that I just went through. So let's take a look at that code. So first of all, I've added two new fields. One is called to target angle, and this is going to be the maximum angle I want to try to turn to at any one time. I don't want the turns to be too sudden or large, and I always want my angles to be gradual. So if the angle necessary to turn toward the target is bigger than this, we'll just make it this angle. Then I want time check to point at target. So I don't want to check every single cycle if I can go to the target. I don't need to, and it's somewhat expensive, and it gives a bit more randomness to have the spiders spread out if I don't check constantly. So I just made it 0.3 seconds. Again, that's just the default. The bigger we do, we make that the longer they'll head in the wrong direction before they try to turn. And I played around with these values just to see what would give me a good spread of the spiders, a group of spiders, as they're all walking toward the target, because I don't want them all to line up. I have some member variables here. I have the nav marker. This is just going to hold the position of the nav marker. I have my nav marker tag, which of course matches that tag value string that I set. And then I have time to rotate to target. And that is going to work in conjunction with this time check to point at target, so that once that value is greater than that value, then we'll check the time. So the next thing I have is I grab the nav marker position, just find game object with tag using that nav marker tag constant that I made. So that will give us that position that we're going to want to travel toward. In the update, what I'm doing is once the spiders have reached the nav marker, I want to destroy them. So in the opening scene of my previous video, you saw that there was a whole group of spiders all crawling. They're generated all in the same spot. They spread out, they walk over the landscape, and then once they reach that nav target, I want to destroy them. So I added that code. So now comes the meat of our addition. So what I'm going to do is on my fixed update, after I've checked and turned or calculated an angle that I need to turn to avoid walking over too steep of a face, I'm going to check our rotate toward target, and Again, I'm going to add this time to rotate. If it's greater than my fixed time to rotate, then in this case 0.3 seconds, it's going to call a function to try to point at target and then set this back to 0. So here's our other functions we went over. So what I'm going to try to do is calculate an angle that will rotate me toward the target if necessary. So what I'm going to do first of all is I'm going to save the current rotation, and I'm going to do this look at function. So look at is a simple function that's just going to turn my object toward whatever point I'm looking at. And of course, I'm going to look at the nav marker. And then what I'm going to do is I want to find the y value. Again, remember y is up, rotating around that up vector to say what is the angle that I need to turn to look at that. So I take my current rotation, which is the way I'm facing. I look at my new rotation, what it is to look at it, and I subtract the two to get this angle. So the question is what is this angle going to be? And what it ends up being is it always ends up being a negative angle. And so if I was facing to the right, it would be, say, negative 30 degrees. If I'm facing to the left, it's going to be negative 330 degrees. So to put that into perspective, just so we can visualize it, if this is my spider and I'm rotated this way, of course, if I need to rotate 30 degrees counterclockwise or clockwise to face my nav marker, I could spin around all the way around 330 degrees and I'm pointing at the marker, or I could turn a positive 30 degrees to turn over the marker. Both will get me there, but I always want to go in this positive direction. I don't want to spin all the way around. And so in order to make sure that I have that, I'm checking to say if it's less than 180 degrees, then I want to add 360 to it, because it ends up this is always negative. So if it's negative 330 and I add 360, it's going to end up being positive 30. If it was greater than 180, I want to subtract 360. I never want to rotate more than 180 degrees, essentially is what this code is doing. So this is always going to give me a positive or negative rotation, the shortest rotation necessary to point at my nav marker. Then I'm going to set my rotation back because I was just using this to calculate that angle. And then I'm going to say my angle to target is going to be this diff angle, because this is what I need to move to rotate toward my target. If it's 0, that means I don't need to do anything. I'm already pointing at the target. Everything's good. If it's less than 0, then what I'm going to do is I am going to take the absolute value, because I want to make it a positive, and I'm going to say, is this bigger than my 2 target angle? Basically, is it going to be bigger than that 20 degrees? If it's not, then I'm going to get the angle to normal for that diff angle. So I'm going to call a function, which I'll go over in a minute. And essentially what this function is going to do is it's going to say, if I turned and traveled in that direction, what is the angle of that face? Remember, we already went over how that worked for that right to left. It's basically going to do the same thing. It's going to say, what is the angle to that face? And down here, it's going to say, hey, is that going to be less than max angle? If it's not, if I turned toward the target and I'm going to try to walk over a face that's too big, or the angle is too large, I don't want to turn in that direction. So I'm just going to do nothing. I'm going to keep walking in the direction I'm going until I can turn and not walk over too high of a face. So then if it's greater than 0, it is going to do this. Remember, if it's 0, it's not going to do either one of these. Actually, 0 would be. It would fall down to this else if it was 0. Technically, I could check if it was 0, I really need to do nothing, but I didn't do that. I added some logs here because as I was debugging it, I wanted to check out what those angles were that was being calculated. That's how I figured out the negative, and I had some issues that I debugged with that debug log. So if it's a positive angle, I basically want to do the same thing. I could have probably combined these in some different logic, but this is how I chose to do it. This is the only thing that's really different here. I'm always going to want to take a negative of that to target angle if my diff angle was too big. So essentially it's going to say, hey, am I less than 20, make it the diff angle. If I'm greater than 220, I'm going to make it the negative of the to target angle, or negative 20 degrees. In this case, it's just going to be the diff angle or the to target angle. So now I have my angle. I have my angle to normal. If it's too steep, just do nothing. If it's not too steep, what I want to do is remember this current rotation Y. The current rotation Y is what we check in order to say, hey, do I need to turn it all? And so if I'm currently turning, it is basically going to modify that current rotation Y or add it to my current rotation. So it's going to, the problem here is that we may already be turning because we've encountered a face that's too steep, and we want to turn toward the target. So both of these, we can't do both of them at once. We want to integrate them together. And we're using this current rotation Y is always going to be the angle where I want to turn. And it may be turning toward the target. It may be turning away from a face that's too steep. Both are calculated independently and then added together. And so this allows me to use one function, which of course we went over. It is way up here in our fixed update. Remember, we're using that current rotation Y to get a rotation, and if that rotation is different than what I'm pointing at right now, which is what this code is doing here, and I'm not already doing a rotation, I'm gonna start that rotation. So the current rotation Y could be calculated from avoiding a steep face, or it could be I'm trying to point at a target, or it could be a combination of those both. The last thing we're gonna go over is that get angle to normal. So that's gonna get this angle to check. Very similar to what we were doing before. It is going to say, okay, I want to save the rotation. I want to get my, transform my rotation from the current rotation times this rotation to the right, which is going to be a vector, not rotating around the X or the Z, but just the Y of that angle to check that was passed in. And remember, multiplying quaternions are just like adding the angles. So I get this new rotation. Now I'm going to want to say, okay, if I moved ahead by a body length, remember, same thing as we were using up above. That's what this transform direction, ahead to check, is that body length. So if I moved ahead a body length in that direction, what would that face be? So I get that point ahead. Then I'm going to use that for my ray cast down, and it's going to grab that angle. And then it's going to set my transform rotation back to what it was, and it's going to return that angle. So essentially this is going to say, hey, give me an angle, see if I can move in that direction, give me the angle of that face if I moved in that direction, return it. So in that case, we will make sure that we're not fighting. If we didn't do this, if we didn't check that angle, we'd constantly be fighting the other calculation. We'd say, I want to move toward the target. Oh, I'm start to move toward the target, but oh, he's too steep, move away. Move toward the target, and they'd be fighting each other. In this case, we want to make sure we never try to turn toward the target unless we're going to go over a face that's not too steep. So now let's go and try to check this out. Let's do the simple one where I'm just going to point not toward the target. Doesn't involve any of the hills, and I'm just going to run that. So he's just going over flat. He should just turn toward the target and then keep going straight. And there he turned. That's good. So now let's rotate him this way. Let's play that. And he turned. That was correct. So now what we're going to do is we are going to move him a little closer so we can change this to our global. Go like that. And let's play. So now he's going to turn, but the hill's in the way. He's going to turn. He's walking. He encounters the hill. He's going to walk around the hill. And then he turned toward the target. Exactly how he's supposed to do it. Then once he reaches the target, what is going to happen is he's going to be destroyed. So now for the final step, we're going to set up our scene of the spiders crawling over this rough surface with some lighting and see how we can put it all together. So the first step is I brought in this test mountain surface that I kind of showed on the very first video, and I removed that test plane that we were using for debugging our script. I have my spider here, so the first thing you need to do is you need to grab that spider and drag it over into your assets somewhere. I always make these folders every time I make a project. I have my imports, which was the original place the spider came in from Blender, and then I always drag it into meshes because you need a prefab, because our code is going to create the spiders dynamically on a timer. So we get lots of spiders coming out from a location. So do that, and now we have a spider over here that we can use to have the code to launch the spiders. Then what I have is I have this spider launch marker. So what I did is I just copied that nav marker. I added a tag spider start because this is where the code's going to create the spiders originally. And we're going to take a look at the code of how those spiders are created. So what I did is my main camera, I have another script that's going to be added to it. So we'll take a look at that script and add it to the camera. So this is the script. It's just called main controller because it's the main script that's going to drive the whole scene. And what I have is I have my spider start tag here. I have my nav marker tag that we used before. I have this spider spawn time. So how many times per second do we want to spawn the timer? So it's going to go every 0.2 seconds. So five spiders per second. It's just going to be the default, and I can change that. And then I have my spider game object. So this way I can drag and drop any object onto this controller that I want to create. In this case, it's going to be our spider mesh, which we have our spider script connected to. And then I have a couple of member variables, spider start, which is just going to be the location, and current spider launch time, which is going to count up. So what we do is we add, of course, to our spider current spider spawn time. We always add to that during the update. And if it's greater than our spawn time, we're going to create our spider. So this is the code that does that. I want to grab and instantiate that spider type. So that spider is this game object that we exposed. So I'm going to create one of those game objects. I'm going to pick a random number between -1 and 1. So what we want to do is we want to get a 50-50 chance of the spider pointing left or right, essentially. We're going to grab our position, which is going to be that spider start marker, plus this X adjust. So I'm going to adjust the position by -1 or 1 in the X direction. Again, we don't want them all starting exactly at the same spot. So they'll give a little variation. Then what I'm going to do is I'm going to grab my nav marker, where I'm going to point to, where do I want to go to, and then based on that X adjust, so again, it's going to be either less than 0 or greater than 0, 50-50 chance. And I'm going to look at the marker. So I want to get the angle. If I wanted to go straight toward the marker, what would that angle be? And I want to point at the marker, and then I'm going to adjust that by -40, a random number between -40 and 5 degrees. So I'm going to make this Y adjust. So I'm going to point him not all at the marker, because then they'd be coming out of the line, but I want to give him a random spread. So I'll change the angle there. If it's greater than 0, I will change it in the positive direction. So essentially, we're going to get 50% of the spiders kind of rotating left by some degrees, 50% pointing right by some degrees. And then I am going to take that Y adjust value and I'm going to apply it to my spider. So essentially they'll start out kind of a random position around that nav marker, pointing in some random angle left or some random angle right. So this is going to get a nice spread, so the spiders spread out when they start. And then I just got some basic keys to to quit the application for Q or escape. Because if you build it as an app, you have to have some way of killing the app. So that's pretty much it for the code. So now what we're going to do is apply it to that camera and run it and see what happens. All right, so I did a couple things to our scene. I added this point light that's going to give our atmospheric lighting. I have currently a directional light on because we can kind of see where do we want to put the spawn marker in order to get a good spread of the spiders and make it a good effect. I played around a bit with it, and so I decided to put it kind of back here. So this is the cameras looking in this direction through this kind of gap. And so by back here, they can get, some of them will maybe go up here, some will go down here. And then what I did is, for our main camera, we want to add that script. So we'll go in here, add our main controller script. Just leave the spawn time at 0.2 seconds. Grab our spider here. Oops. Grab our spider, drag it down over our game object. You can also hit this little lock here. We'll make it so it doesn't flip between when you click and release like that. So now we have our nav marker, we have our main camera. So let's run. What we can do is we can go to this scene. We can kind of watch the spiders come out. So you can see they're starting at different positions on that x-axis. They're starting at different angles. Some are kind of going in this direction, some are kind of going in this direction, and they hit these faces and they decide which way to go. So that's a decent spread of the spiders coming out. I did modify the angle, so the left angle I made 70, so they can kind of go up this face here. The right angle is 60. All the other ones are defaults. You notice on some, they're trying to find a face and they kind of turn in circles, so some of them kind of get lost here. This guy's turned in a circle, which is fine. And let's go to our game. So this is what they look like coming out. That's pretty good. So now if we go into our directional light, let's turn off that light. Go back to the game scene. So this is what it kind of looks like. Our point light, I have it at 23 intensity. Maybe if it's not bright enough, or if, say, we want to, let's go back here, we can adjust its position in order to get kind of the look we want. Now let's run that guy. So we see the eyes of the spider glowing. Remember, those are unlit, so we're going to see them. Kind of cool effect in the background. That all you see is the glowing eyes of the spiders kind of coming out from that spot. And then as they kind of come into the light, they start to light up, and we can see them up here. So I kind of like how some are coming over that spot. Some are kind of coming over this spot and take different routes. So that's that. So now we got our effect. Most of the work was trying to get these spiders to crawl over the irregular surfaces correctly and align themselves. Looks pretty good. So overall, this is a cool effect for a game if you want a swarm of small enemies to kind of come out of a spot, kind of crawl over some rocks toward you. I think it can make a cool effect. So again, this covered a lot of complex rotations. I do have the links to my other rotation videos if you need more practice and understanding exactly how those quaternions are working. And stay tuned for my next video. Thanks for watching.